Okay, so let's continue with an example. Now this one is for table lookup, and it's a very simple example. So it's for like a square table, right? Square means x squared, x to the power of 2. And you might think, huh, why would I ever want to do this? Couldn't I just use multiply? Well, you could, but I suppose there are times when the table lookup actually can make more sense. So, for example, if you have to use something like trigonometry, like cosine and sine, tangent, um, those actually can be very computationally intensive, especially if you don't have floating point support. But if you have a lookup table, which actually was what I had to do when I learned trigonometry, we had to look up the sine and cosine table and up to a few digits. Okay, then this actually is a good technique. Okay, um, so in C language, you might do const int, or it could be maybe not an int, maybe a char, right? You can do 0, 1, 4, 9, 16, 25, 36, 49, right? So those are the x squared, right? So instead of doing a multiply by itself, it's actually easier to, for the little microcontroller anyway, to do a table lookup. And one thing you can do here is to write it in assembly like this. So remember dB, that's to define byte. You can define a sequence of bytes or a sequence of whichever. It could be a string, right? So that would list its ASCII code. So basically you put the products in there, right? So 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. And then to do a table lookup, what you can do is then first load the address of the table, which is written with a pound sign table, right, into DPTR. So that loads the 16-bit address in code space. Remember, this is code space into the DPTR. And then to do a lookup, you would load the number into A. Where does this number come from? Well, for now, let's just assume comes from P1. That's an I/O port. So assume somebody has the bit pattern in P1. You just read it and then put it in A. And then you do movc A comma at A plus DPTR. So A plus DPTR basically says take the address at a table and then whatever A is, add it, right? And then that forms your effective address. So that will index it into the proper location, right? And then if it's 5, then it indexes by 5. So that adds 5 to the table address, and then that loads 25. Once 25 is loaded in from the code memory, it puts it into A. Okay, so it replaces the A itself with the A squared. So that's a simple example of table lookup for squaring a number. And then you can do something like this. If you want it in a loop, you can basically keep loading some number from P1, square it, and then output it on another port P2, and then keep looping. Okay, so that's just a simple little example. Now, movc versus movx. So both use the DPTR. So you have to load the 16-bit pointer. They are different spaces, right? C code space, that's for execution, and that's actually read-only. So you can do execution. You can run code from there. You can do a constant table lookup like that, but you cannot write to it. At least not with regular instructions. If you ever have to program it, then there are usually other special function registers that let you write to the code memory, but not using movx instruction. In fact, there is no movc instructions for storing things. They're only loading into A, but not writing from A to code memory. In 8051, that combination does not exist. But movx has both reading and writing. Okay, and as you recall, this is a Harvard architecture, so the address spaces for code and X data are separate. Now, there are always exceptions, and most 8051 architecture implementation that I know of have some ways of mapping some parts of data space into code space, including the CC2540 chip that we'll be using. And that allows you to do a variety of things which we'll talk about. And it's convenient to be able to do that, especially if you're running code from flash memory. And one of the things is if you want to be able to program the program memory itself, that is, do bootloader or to update firmware by the program itself, then it may have to switch to running in data space, because during that time you're writing to the flash memory and you can't read from it at the same time. But we'll talk about those more advanced features later. And some may think, well, just having one DPTR is not so convenient, right? Because at least with iData, you have R0 and R1 that you can do at R0, at R1. So you have essentially two pointer registers, but DPTR is just one. Yes, that's actually true. And in many other 8051 architectures, they define additional DPTRs. There's DPTR2, DPTR3, possibly, and those will make it easier, either by hand or by compiler, to generate more efficient code. But that's not in the original 8051 definition. Okay, so just a summary. So iData space, original 8051 from 0 to 7FF, that's for data. You can do direct addressing or indirect addressing, right? So either the R or the at R, 0R1. Now 82FF, that's for SFR only, and that's direct addressing only. In 8052, now the space from 0 to 7F, that can be direct addressing or indirect addressing, just like the original 8051. But in the 80 to FF space, if it's direct addressing, then that's SFR. If it's indirect addressing, then that's data. Okay, so that part I think should know about. And just the last comments. So the upper 128 bytes in the 8052, that is actually pretty common for use by the stack. Because it's accessed indirectly only. That means only through R0 or R1 or stack pointer. Okay, and because the original 8051 uses the space that is from address 8 and up, and you don't want to overlap the bit addressable space, which is at 20. That's not a lot of stack space. So after a few function calls or subroutine calls and passing some parameters, you run out of space very quickly. So one common practice is to have the stack starting at this space, and that way you can actually support more stack depth and maybe local variables and other things. Okay, so and this allows you to separate the stack from registers, bit memory, and other global memories.